Welcome. My name is Shlomi Steinberg. I'm a PhD candidate at the University of California, Santa Barbara, and I will be presenting our paper, A Generic Framework for Physical Light Transport. The purpose of this paper is to generalize the classical radiometric light transport to physical optics. In this presentation, I will be discussing the nature of light and briefly describe the ideas that we develop in this paper. For more information, please see the paper. We also provide an extensive supplemental material where all the relevant physics and mathematics are derived and may serve as a reference. Okay, so let me start. As we know, in computer graphics, the prevalent model of light follows a radiometric description, which means that we deal with units of power. And as a consequence, the wave nature of light is ignored, and light propagates along straight geometric lines. This is a useful simplified optical model, which we commonly refer to as geometric optics or ray optics. This formulation of optics has been tremendously successful in computer graphics, both for offline and real-time rendering. This success, however, has been mostly confined to multimedia applications. A more physical, so to speak, description of light is by understanding light as an electromagnetic wave. Under such a model, light propagates in accordance to Maxwell's celebrated equations of classical electrodynamics, and this model of light is able to describe accurately a wide variety of diffraction and wave interference effects. In computer graphics, we have been applying electromagnetism locally. That is, while ignoring the light wave's nature, we source light from a light source and transport it throughout the scene. Only once we encounter a material whose appearance reproduction requires accounting for wave interference effects, we recall that light is in fact electromagnetic waves and model the wave optical interaction locally. Afterwards, we revert back to classical light transport to propagate light away. In this fashion, we are able to reproduce the appearance of a variety of materials where wave interference plays a major role, but only under specific predetermined illumination properties. Let me explain. Consider the following soap bubbles. They have similar chemical composition and are illuminated by light with similar spectrum and intensity. Nevertheless, interference effects are clearly visible on the right and virtually not at all on the left. Similarly, a compact disc illuminated by the same light sources as before, both sources radiate with similar spectrum and intensity. But, while the primary diffraction lobe is visible in both photos, secondary diffraction lobes only appear on the photo on the right. So, what's going on here? The reason for this phenomenon is a partial coherence of light, and without going into too much detail, coherence is a statistical property of light, and to understand coherence, we have to consider the wave nature of light. Light in practice is composed of very many individual waves. If the waveforms of these waves are similar over some space-time region, as illustrated in the right image, then we say that the light is coherent and is able to reproduce constructive and destructive interference effects. Otherwise, if the waves include uncorrelated random fluctuations, then we say that light is incoherent. In this case, constructive and destructive interferences cancel out on average, and no interference phenomena would arise. In addition, at optical frequencies, we do not observe the individual oscillations of light, but only time average values. For example, the following two waveforms, as functions of time, will appear identical when observed using a typical camera or the human eye. Then, we can summarize with saying that the study of the coherence properties of light is a study of the observable properties of light, because the intensity of a light beam that we observe or measure is in fact the time averaged intensity. And the statistical similarity between the waves that compose that light beam quantify the magnitude of the interference effects that appear. It is these statistics that govern the propagation of light, its interaction with matter, and its observed properties. Therefore, in our formalism, we adopt a purely statistical model of light. How then do we analytically model these statistics? The core quantity is a temporal Fourier transform pair of the second-order statistical moment of the random process that describes light. This quantity is known as the cross-spectral density function, CSD for short. The cross-spectral density of a light beam can also be understood as classical radiance, multiplied by the spectral degree of coherence function. This degree of coherence is a function of wavelengths, as well as a pair of points in space, and it fully quantifies the coherence properties of the beam. The complex magnitude of this degree of coherence functions takes normalized values between 0 and 1, indicating how statistically similar are the waves that arrive at the two space points x1 and x2. This two-point information is crucial. High statistical similarity between light waves that reach the 2 points x1 and x2 means that scattered light from these points may superpose to produce visible interference effects. On the other hand, when that light is not statistically similar, then on average the scattered light will not produce any observable wave interference effects. And remember, it's not the instantaneous flux that we observe, but only time averaged values. It can be shown that this two-point information is necessary for a formalism that is consistent with electromagnetism, which implies that classical radiance-based description of light is in fact inconsistent with electromagnetism. Furthermore, our formalism is indeed powerful enough to describe observable optical phenomena because we observe light over long periods. That is, over the course of one such observation, many statistically independent waveforms contribute to the perceived intensity. Thus, the central limit theorem may be brought to bear, and we can conclude that second-order statistics are sufficient. Therefore, by replacing the classical radiance with these cross-spectral density functions, we get an optical formalism that is able to reproduce essentially any observable optical phenomenon that can be reproduced with partially coherent light and explained via the theory of electromagnetism. Okay, so this is a powerful theory, but how do we transport these CSD functions in practice? Let's recall the classical rendering equation, which relates the excitant, emitted, and incident radiance via the BRDF using a linear integral equation. While in general solving this equation is not a straightforward task, current work that does tackle this problem takes advantage of the linearity of this equation. In the paper, we derive a similar integral equation for the transport of CSD functions, and it takes the following form. We term this equation the spectral density transport equation, SDTE for short, and what we have done is replace the radiance values with radiance-carrying CSD functions, as well as replace the BSDF with some diffraction operator, which acts upon those CSD functions. I will very briefly talk about the diffraction operator in a moment. Of more importance, however, is the fact that this equation remains a linear integral equation. This is of value because it suggests that some of the state-of-the-art that aims to solve the classical rendering equation could also be adapted for our formalism of physical light transport. So how come this equation remains linear? Recall that the cross-spectral density of a sum of independent stochastic processes is simply the sum of their respective CSD functions. Assume that we have two different sources of light. These can be primary sources or secondary sources, where a secondary source is, for example, a reflection of a surface or any scatter of light by matter or media. Then, the CSD of the superposition of light from these two sources is going to be the linear combination of the propagated CSDs from its source, because they are statistically independent. The driving principle is then the fact that the light we use is rather weakly coherent. If a pair of light passes deviate by even a fraction of a millimeter, then the energy carried by these beams of light is mutually incoherent, and they superpose linearly. This realization allows us to derive a formalism of light transport that is driven by a linear transport equation and is fully consistent with classical electromagnetism. An important theoretical observation is that our formalism generalizes classical light transport in the sense of the short wavelength limit. We formally prove so in the paper. The main differences with classical light transport are: 1. Because a CSD is a function of a pair of points, this CSD needs to be defined in a small region, and we now propagate beams of light region to region, in contrast to point. Furthermore, 2. Because a core quantity is now a function, the CSD, in place of a value, the radiance, any operation that we perform with light, propagation, interaction of light with matter or media, and measurement, are all modeled via operators that act upon and mutate these CSD functions. This brings us back to the diffraction operator that we saw in the spectral density transport equation. This operator models the physical process of light-matter interaction. Conceptually, this is not very different from classical theory. Given light incident from a direction, that operator models the interaction of light with matter and describes the scattered light. Computationally tractable light-matter interaction under physical optics is a rather large topic by itself. A more comprehensive discussion has been left for future work, and good progress has already been made. In this paper, we only discuss a few special and simplified cases of light-matter interaction, including the sourcing of light, a measurement of light, reflection and refraction with respect to the Fresnel coefficients, and slightly more involved, diffraction by an explicitly defined surface. We show that under our formulation, this interaction with an explicitly defined surface reduces predictably to a simple spatial convolution. This formula admits similar computational complexity to the state of the art, but unlike the state of the art, we can formulate interaction with light of virtually arbitrary coherence properties. Additionally, we can render the diffraction grating of a compact disk under illumination by light sources with different coherence properties. As with the photographs before, while the primary diffraction lobe is well visible on both, secondary lobes are far more pronounced on the right. We can also render more complicated scenes. For example, a scratch bronze statue is illuminated by a small light source. The illumination of the upper part of the statue is dominated by direct incident light, and therefore visible, colorful diffractions appear. On the other hand, the bottom part is dominated by light that is diffused by the water in the vase, and that light loses some of its capacity to interfere and produce visible diffractive effects. I would also like to very briefly discuss applications. Beyond photorealistic rendering, a light transport framework that is consistent with electromagnetism opens up all kinds of applications in the domains of scientific visualization and computational electrodynamics. Traditional wave solvers are known to be notoriously slow, and especially so when dealing with partially coherent light. The linearity of our framework strongly suggests that we could apply some of the modern rendering tools to the study of propagation of electromagnetic waves in complex environments, like urban settings, where traditional optical tools are simply intractable. For example, Wi-Fi and cellular signals are nothing more than partially coherent light of non-optical frequencies. Likewise, propagation of different kinds of radar, for example for assistive driving technology and defense systems, can also be understood as rendering with partially coherent light of non-optical frequencies. Finally, a few constraints are worth mentioning. I will stress again that the driving assumptions are weakly coherent light and observation over times long with respect to the temporal coherence of light. In practice, these two limitations are almost always very well satisfied. Of practical importance is the fact that we propagate functions and not numeric values. These CSD functions initially depend on the source. They drive, as described, the physical process of light-matter interaction, and in turn, that process mutates the coherence properties of the scattered light. This means that these CSD functions can take a wide variety of shapes and forms, but we want to avoid an impractical symbolic treatment. So how to practically represent a large family of relevant CSD functions has been left for future work, and some good progress has already been made as well. Also, because the interaction of light with matter depends on the coherence properties of light, we require this coherence information in order to quantify, sample, and understand what happens at the surface or medium. Therefore, we are limited to tracing from the sources, as only this way we can propagate the coherence properties of light. This information is not available when tracing backwards. While a full bidirectional path tracing can not happen with physical light transport without making significant approximations, future work does indeed relax this constraint to a degree without compromising the accuracy. Alright, that's all I have to say. Thank you very much for listening. Please see the paper for more details, as well as my website for up-to-date information. Also, the SIGGRAPH Research Career Development Committee is a new organization that aims to promote and advocate for the computer graphics research community. We are actively looking for mentors for all career paths and stages. For more information, please check the website and feel free to contact me. Thank you.